Thank you very much for having me. It's a pleasure to be here. Quantum, we got the slides coming up? Quantum computing is getting a lot of attention these days. You know, you can read lots of headlines. I picked a couple to start with here. First of all, China just announced they're going to spend $12 billion on a center for quantum technology, which includes quantum computing. If this happens over several years, I imagine, this will be the largest investment, probably larger than all of the investment made by the entire world in quantum computing. It's pretty easy to pick out headlines that talk about how quantum computing will affect the strategic balance in the world, military, commercial, intelligence, and you know, there's just huge implications of developing quantum computing that are being recognized. Morgan Stanley just published a report that says quantum computing is a must-have for global productivity as we go forward, and that it will likely kick off the fourth industrial revolution. And then they go on to talk about applications in virtually every industry you can think of. Machine learning, energy, climate modeling, cures for cancer, materials design. Every industry is a potential application for what's happening in quantum computing. By the way, if you go pull this Morgan Stanley report, be a little skeptical of some of the details, but the overall conclusions are pretty sound. They're not necessarily experts in quantum computing who wrote the report. One thing you'll notice if you do the research and read the headlines is that you'll find lots of headlines about quantum computing, about companies that have nothing to do with D-Wave. There's usually a photo of a D-Wave system or a D-Wave processor in those stories, because there's actually only one quantum computer today. And so what I want to talk about is how does this work, what's coming in the next few years, and how does D-Wave fit into it, and sort of what does it mean in the nearer term future. You may have noticed our tagline is quantum computing for the real world today. First of all, why is quantum computing getting so much attention? Because we all know that Moore's law, the end of Moore's law articles are almost as common as the articles about quantum computing or artificial intelligence. Moore's law is coming to an end. Classical computing is reaching its limits. There are lots of very smart engineers figuring out how to make things more efficient, but there are fundamental limits in classical computing that we're starting to run into. Quantum computers have the potential to scale exponentially, and that's not exponentially like Moore's law. Moore's law is we double the number of transistors, we double the number of operations, and we scale exponentially like that. Quantum computing scales exponentially on top of the number of qubits. So we are actually expanding the number of qubits exponentially, just like Moore's law, doubling every 2 years. The power of a quantum computer doubles exponentially on top of the number of qubits, which I'll explain more in a second. A little bit of quantum computing 101. How does this work? With a classical computer, the calculations are sequential. Each bit has to be exactly 0 or exactly 1, and you have a big problem if the bits actually interact with each other. The calculations get faster and faster and faster, but they're essentially sequential calculations going faster, faster, faster. It's like one person with a calculator who has a finger at the speed of light, but there's only so fast that can go. With a quantum computer, we shift from classical bits to what we call qubits, which are quantum bits. Quantum bits take advantage of the properties of quantum mechanics, which are not intuitive. We can have bits that are 0 and 1 at the same time, and we plan to have interactions among the qubits. So 0 and 1 at the same time is called superposition. The interaction of the qubits is called entanglement, two of the key properties of quantum computers. And because of those properties, the power of a quantum computer scales like this. If we add 1 qubit to a quantum computer, we double the power of the quantum computer. Or another way of saying that is, a quantum computer can consider 2 to the n possibilities at the same time. So if we have 100 qubits, we can consider 2 to the 100th possibilities at the same time. and then figure out an answer. Just to put that in perspective, 2 to the 270th is the number of particles in the known universe, the number of atoms, essentially, in the known universe. So if we have a quantum computer with 270 functioning logical qubits, you can have a computer that can consider all of the possibilities, as many possibilities as there are particles in the known universe, all at the same time, and do that over and over again. So the power, the potential power, is staggering, and that's why there's so much attention. So what happens in a quantum computer is we take the qubits, we excite the qubits, and then we observe the final state. When you observe, it flips back into classical, we read out the answer, we get an answer, and we go on. Let me give you just a little more intuitive feel for how this works. Many problems that are really important in computation and business have the characteristic of a maximization or minimization problem. So think about a simple two-dimensional problem you can put on a graph. A three-dimensional problem you can think of like this picture. These problems are n-dimensional. And so we could have problems that are hundreds or thousands of dimensions, and we want to find the minimum, all the variables interacting with each other. And the problem is, find the lowest point. If I have a classical computer, think about a person who runs really fast, who has to go out and climb around the Alps, and every time he or she gets to a valley, think, am I at the lowest point, or should I climb the next mountain and look for a lowest point? That's essentially the way a classical computer solves this problem. A quantum computer, it's hard to come up with perfect analogies, but a good analogy is, imagine I had 1 trillion tiny little drones, and these drones could sense altitude and talk to each other. I throw the drones into the mountains, they instantly cover all the mountains, they communicate with each other, the one that gets to the lowest altitude wins, boom, everyone stops. That's essentially what's happening in a D-Wave quantum computer. It's an analog device for solving that problem. Now, these are the kind of problems that scale exponentially. And so it's very easy to find problems like this that would take the age of the universe to solve if we tried to solve it precisely on a classical computer. So the device that D-Wave makes is called an annealing quantum computer. It's an analog device which looks like this. That chip in the center of the holder is about the size of a fingernail. It has 2,000 circuits, what are called the 2,000 qubits. So the qubits are small, but they're still macroscopic. By the standards of semiconductor manufacturing, they're gigantic. These are not small by tolerances of semiconductor manufacturing. And we use those techniques to manufacture the chips. So we know we can continue to scale this because of the manufacturing process. On the right is a blow-up of one cell from that chip, and the qubits are highlighted. They're loops of niobium metal. We take it down to about 1,000th of a degree above absolute zero. They become superconductors. Current runs in 2 directions at once, and you have superposition. And then we entangle the qubits, and we can set up this processor to run the kind of calculations that I talked about. I want to give you just a sense for how what D-Wave does fits into the overall efforts going on in quantum computing. We started out with the headlines about the miraculous things that quantum computing will be able to do. Well, when will that happen, and how is it going to work? We have really 3 basic approaches to quantum computing. There's a gate model of quantum computer, which is being pursued by some very large companies with a lot of resources. These are essentially designed like classical computers with logic gates, but each logic gate is quantum. Now, in order to do that, we have to manipulate individual atomic particles. We have to take an electron or a photon, excite it, manipulate it, keep it there, and then read out the answer. It's really hard. The people building these systems are all on record as saying it will be at least 10 years before there's a useful commercial device, or a device that potentially could be commercially useful. It's very, very hard to scale that approach. Microsoft is doing something very similar called topological quantum computing. Essentially, it's a gate model computer that relies on a 2-dimensional quasi-particle which has only recently been proven to exist. So, you know, it's very interesting because it doesn't require error correction the way a gate model computer does, but it's further off in the future. Error correction is a very important subject when we talk about gate model computers. If we have a gate model computer with roughly 1,000 physical qubits, that's going to mean that there's about one logical qubit in that computer. So there's about a 1,000 to 1 ratio between physical qubits in a chip or in a device and the actual logical qubit that you can do real work with. D-Wave chose a different approach, this annealing approach, because it's relatively easier. What we're doing is really hard. It's taken us 17 years to get to where we are. But it's relatively easier than building a gate model computer. The advantage is it is easier, and it can handle most problems that we would want to solve with any quantum computer. Just to put this in perspective, in the last 10 years, D-Wave has gone from a handful of qubits to 2,000 qubits, and we're already making prototypes to double the number of qubits again, up to about 4,000. The gate model community has gone from 9 to 22, and that's with a lot of resources, a lot of very smart people, so it's hard. In addition to manufacturing the qubits, there are a lot of other technologies that are critical here. In order to build these systems, we have become the world leader in superconducting semiconductors. We're probably the world leader in refrigeration technology. We have to get information in and out of this extreme environment. The environment we create has essentially no temperature, no radiation, no magnetism, and a perfect vacuum, and no vibration. We have to design systems that will get information in large volumes in and out of that environment without disrupting the environment. So we have over 150 patents in all of these technologies. ULIC, the ULIC Superconducting Center is the German equivalent of, let's say, Los Alamos or Oak Ridge in the US, which, by the way, are our customers. We sold systems and access to both Los Alamos and Oak Ridge. ULIC has very carefully studied what's happening in quantum computing. They've studied our system. They've studied the other systems that are available, like the IBM gate model system, which is available in the cloud. They developed this technology scale. I won't read you, but you can imagine it goes from the bottom, which is an idea, up through the top, which means we can outperform every classical computer on Earth. D-Wave's not quite at the top yet. They rated us a number 8. Every other device which is available in a laboratory somewhere is rated 5 or below. And so this is, you know, a third-party sort of statement about what's happening in quantum computing. We're getting very close to the point where we can outperform classical. Everybody else is trying to integrate their devices and actually prove that they work. We have $50 million of systems serving customer needs today. We've actually sold $50 million worth of systems that look like that. That photo is actually from our headquarters in Vancouver, because no customer has more than one system. We have about a dozen up in our facility in Vancouver. The bottom picture is at least one form of gate model device as of July of this year. There are other gate model devices that look more like chips. But as I said, every company working on gate model devices has said they're at least 10 years from being commercial. So what can we do today? Here's a list of problems, real problems that we've solved with our systems. So these are hard problems, things like portfolio optimization, matching molecules for cancer cures, drug design, machine learning tasks like image recognition, distinguishing a wink from a blink for Google glasses. So there's a long list of applications. Where we are today is that these are not quite at commercial scale. So we've solved very hard problems, but we can't yet handle problems that are large enough to outperform all the classical computers that run similar problems. We're getting very close. So on this graph, what I'm showing you is that for benchmark problems, so these are problems designed to have the same structure as these hard problems, but they're benchmarks. They're not real-world applications. We've shown several times that we can outperform any classical computer that there is. For commercial problems, so you just think of that list I just showed you, but just scale them up. We're not quite there. We're moving in that direction. So how do we go take that crossover where quantum computers will outperform classical computers on the real problems? We'll build more powerful systems that are easy to use. So essentially that means better processors and better software, all of which is in process at D-Wave. One of the key applications will be machine learning. We heard this morning about machine learning and how it depended on NVIDIA chips, on graphic processing units. The next generation of machine learning models, which are probabilistic models, will actually be much more powerful than the machine learning models being used today. The calculations don't parallelize on GPUs the way the simpler models do. They're a natural fit for D-Wave's quantum processing units, and so we expect that to be one of the primary applications. As we develop these types of applications, we don't expect quantum computers to replace all the classical computers. We expect them to be co-processors. So if you think about GPUs, FPGAs, tensor processing units, those are all specialized processors. So the D-Wave system is a specialized processor too. It can handle very large problems, but it'll be part of an integrated system that will be delivered over the cloud. We actually sell cloud access to our systems today, and we're moving in the direction of more hybridized systems to solve these problems. These are some of our customers. As I said, we're selling cloud access today. You can read our press releases about some of these customers. The ones on the left actually have either purchased or leased systems and have them on premises. We expect some of that business in the future, but there'll be much more emphasis on delivering these services as hybrid services through the cloud. Just a quick advertisement for D-Wave here. I was told this is not a financing pitch, but there's a few facts about the company. It's up in Vancouver, 160 people, 45 people with PhDs. We've raised $200 million. We will need more capital, although right now we're good because we closed a $50 million commitment with PSP, a large Canadian pension fund, in April. But as we grow, we certainly will need more money, so maybe we can talk to some of you about that. And I think I'm a little over time. I apologize for that, but thank you very much.